Today we're continuing on Unit 6, Lesson 1. We're on Day 2. We're focusing on all the different operations with vectors. So we're going to look at adding and subtracting them in a couple different ways. We're going to look at scalar multiplication, something called a unit vector, and a few applications. And I'm using a different camera, a new one, so we'll have to kind of bear with that. All right, so first thing, I cut and pasted a definition and it kind of came out blurry. But if you're looking for the sum, or what they call the resultant vector, you're literally just adding, if you take a look, the x components and the y components. We're going to use this example that we're given here. So if we are asked to add -1, 3 to 4, 7, as I said, we are literally just doing -1 plus 4. We're adding 3 plus 7, and we end up with components of 3, 10. Now, how can we go and look at it from a graphical standpoint as well? So, two ways we can do it. The first one is called the parallelogram method. So let's take a look here. We have been given the vector -1, 3. So -1, 1, 2, 3. And then we've been given the vector 4, 7. 3, 4, 5, 6, 7. So basically, if we form a parallelogram, we know the opposite sides are congruent. So we would have these two sides are congruent, better extend it a little bit. These two sides are congruent. And so the resultant vector is actually the vector that's sitting in the middle of those. Okay, so the resultant vector is the final answer. So from here to here, it should correspond with 3, 10. If we had some graph paper, it would make it a little bit more accurate, but we're going to go with it. Okay, the second method, how we can add and subtract graphically, is the tail to head. So again, in this particular case, we would draw a vector which was -1, 3. And then from there, we add on that vector which would be 4, 7. So that means we are going to the right 1, 2, 3, 4. So from here, we're going 1, 2, 3, 4, and then we're going up 7. And again, from here to here is that resultant vector, and again, we should end up with the components 3, 10. Now, obviously, just adding the components is the easiest way to do it, but oftentimes we'll see where there's examples where it might be beneficial to look at it from a graphical standpoint. And the only other comment I want to include up here is when we are adding or subtracting, the vectors have to be in component form. So let's write that down. Must be in component form. Next, we're going to look at scalar multiplication, and we actually saw scalar multiplication back when we did matrices. It essentially meant you took a scalar, which they're going to give you, and you multiplied it through every element in the matrix. So the same thing is true here. Notice if you have KU, U is the vector, so and K is any real number. And U is the vector, then you just take the elements of that vector and you multiply it by K. So for example, if we had 3, 2, 1, then we would just end up with 6, 3. And also kind of relating it back to when we graphed, that 3 is simply stretching that out by 3, both vertically and horizontally. So let's take a look at the example that you've been given. In this case, we've got 3 times vector u and a -2 times vector v. So let's write all that out. We've got 3 times vector u plus -2 times vector v. So that gives us -3, 9, -8, -14. And finally, we're just going to add again the corresponding elements. So we're adding the x components and we're adding the y components. And let's just give you one more little visual here. So if I had the vector 2, 1, 2, 1, and I'm stretching it by 3, then I'm going out 3 units, and that should correspond, obviously my picture's not very good, but it should correspond with 6, 3. Okay, the last operation that we'll look at is something called a unit vector, and again I just cut and pasted this. It said a vector u with length, remember that's not absolute value, but with magnitude 1 is called a unit vector. So we're going to take a vector and convert it to a unit vector. In other words, we want that magnitude to be equal to 1. So let's look at this example here. And let me write this out. So we've got v is equal to the magnitude. So to write it as a unit vector, we take the x-coordinate, we divide it by that magnitude. We take the y-coordinate, we divide it by that magnitude as well. So we're looking for the unit vector for v. So first thing we want to do is go ahead and find that magnitude. And remember, that is the square root of the sum of those components. So in this particular case, we would end up with radical 65. So if we wanted to write this as a unit vector, we would do that as 4 divided by radical 65 and 7 divided by radical 65. Let's take this concept one step further. If I can relate it to anything, it would be like we're trying to place this on the unit circle. So in other words, if you think about the unit circle, it's called the unit circle because your radius is equal to 1. So let's verify that this would be equal to 1. So in other words, we've got 4 radical 65 squared plus 7 over radical 65 squared, and we're trying to verify it's equal to 1. So when I square this, we've got 16 over 65 plus 49 over 65, which means we have 65 over 65. So we're confirming, in order to be a unit vector, that its magnitude of that vector has to be equal to 1. In this particular case, it's radical 65, so it should make sense that all we're doing is dividing each of those by radical 65 in order to get that magnitude to be 1. Okay, let's go take a look at a couple applications. The first one, we've already been given the picture. And one thing that I found in your book, just to kind of help with some of these applications, it talks about velocity as a vector because it has magnitude and direction. And many of you said you've taken physics, so this is where you probably saw it pretty heavily in physics. And the magnitude of velocity is speed. So we take a look at the first one. We've been given a bearing of 65 degrees. Remember, that's from north, and then they've labeled that other angle to be 25 degrees. 500 miles, remember the magnitude of velocity is speed, so that's why we've labeled the magnitude of the length of that vector to be 500. We have to find the component form. So this really goes along with what you did yesterday, but since we're doing applications. And if you remember, you have a formula to find the components. It is magnitude cosine of theta, magnitude times the sine of theta. The only thing you have to remember is when you're plugging this in your calculator that theta has got to be in polar form. So we don't want to use the 65, we want to use that 25. So we've got 500 cosine of 25 degrees and 500 times the sine of 25 degrees. And when I plug that in my calculator, we end up with 453.2. Lost a decimal in there. 453.2, comma to 11.2. And that's all they're looking for, because notice it said again, component form. Okay, let's move on to the next one then. So you've got a plane, and then you've got a wind going along with it as well. And let's go ahead and draw out that picture. I'm just going to pause just to save us a little bit of time. Okay, so I went ahead and drew. It says the plane is going directly due east at 450 miles per hour. You have a wind that's acting on it at 60-degree bearing at 65 miles per hour. So first of all, let's address it. If it's 60-degree bearing, that means we have a 30-degree angle. So what we're really looking for is the resultant vector, which would be from here to here. So let's go right to begin with a vector for the plane. Remember, it is magnitude, comma, the angle, and the angle is 0 degrees with respect to the unit circle. And then let's go write a vector for the wind, which is 65 miles per hour, and its angle is 30 degrees. Now remember, we put on our notes when we're adding, they have to be in component form. So I'm going to go change each of these to component form. So this would be 450 cosine of 0 degrees, 450 sine of 0 degrees. And then I'm going to have to go do the same thing over here. We've got 65